Estamos ao vivo, pode dar início, Fernando.
Great. So welcome everyone, and welcome the committee. I'm very thankful that you took your time to participate on this doctorate defense of Pablo Oliveira. And I would like just shortly introduce the people from the committee. So Professor Renata Simão from Federal University of Rio de Janeiro, Professor Eduardo Cisternas from Temuco, Chile, Universidad de la Frontera, Professor Jorge Aníbal Bosconovitch from the Brookhaven National Lab, and also Professor Túlio Rocha from the Light Source Series and actually like the CNPEN in Campinas. So I'm very thankful that you took your time to participate and bring your comments and your scrutiny based on your expertise in different fields of experimental and theoretical physics. So we are here to listen to the doctorate defense of Pablo Ribeiro Alves de Oliveira. He's from Vitória da Conquista, that is a city in the state of Bahia, and he did his graduate studies in physics in the Universidade Estadual do Sudoeste da Bahia. And he has been working with in my group during the master and now the doctorate, and he has been very successful in his PhD courses with notes and so on, and therefore he got this fellowship from the State Foundation of Rio de Janeiro, FAPERJ Nota 10, which is very welcome acknowledging here. And during his PhD thesis work, most of this work that he's going to present was done here in the CBPF, in our research group, Interface Science Group. But he spent a period of 6 months in the Brookhaven National Lab. We're going to see also some of these results in his presentation, and with the guidance of Professor Aníbal, that is also here in the committee. I would like also to mention my special thanks for Professor Pedro Venezuela from the Federal Fluminense University, because he was very active in guiding Pablo since the beginning of his studies on this part that is also present in his thesis that's related to the DFT calculation and so on. So I'm very thankful that he was for the opportunity and the opportunity to collaborate with him. And I would like just to remind Pablo that he has between 40 and up to 50 minutes to present his thesis, and later on we come to the questions. Okay, so Pablo, please.
Okay, thank you for nice introducing, Fernando. And first of all, thank you for the committee for coming. And this morning, I'm going to show part of my thesis results that I've developed over the past 4 years at CBPF, as Fernando said, and also in a short period at Brookhaven National Laboratory. And basically, we explored the defect engineering on the ZNS surface, and we tried to address how the defects impact the electronic structure, the optical properties, and the surface reactivity from a solid-state physics perspective. I had the pleasure to work under the supervision of Professor Fernando Savalli, and we developed some works in this field that I will try to briefly mention all of them in the next 35 minutes, I guess. So here's the outline I'm following today. First, I will try to motivate the audience on why ZNS is relevant to, and what are the main properties that the system display, and of course, what are the big issues that you should to lead with. And then I move to the methods when I explore both experimental and theoretical tools to address surface size properties of ZNS, and also comparing with the outcome for the experiments with the modeling from the first principle basic DFT calculations. And the third part, I'm going to move to the main resultant discussion, which covering the problems derived from this thesis, which basically I will try to address how defects can improve electronic response of ZNS, if they play a role on the optical properties, and if it is possible to get some reactivity on this system, which is not which was not done before this thesis. And in concluding, I will wrap up my presentation just showing off some general remarks. So let's start for the first point. Here the sentence seems strong, but it is true. Usually, real-world challenge always meet solid-state physics. What I mean is, if you try to figure out about the advances in our field, like the computational methods, about the new devices like diode, emission light, we are always looking for materials with some capability to overcome some challenges. So nowadays, in the real-world challenge perspective, we have some questions that has drawn the attention of the scientific community. Most likely, how to boost the hydrogen storage. It's like looking for platforms for separating the hydrogen from oxygen in the water splitting reaction. How to improve the efficiency of solar cells. So currently, you are most likely working with silicon-based photovoltaic system. So, but silicon is not that good unless of the cost to work with this. And of particular interest, we must to control the rates of emission of greenhouse gases. So all these real-world challenges are translated into the solid-state perspective by questioning yourself, which materials display suitable valence band adds and conduction band adds such that you can split up the water molecule into hydrogen and oxygen. Also, in the perspective of the light interacting systems, how can I turn in the gap of these materials such that you can have a wide range of absorption and emission light. And in terms of reactivity, we are looking for new platforms that display available active sites, because if you don't have active sites, there's no way that the reaction take place. So we are leading with the seeking for new platforms to overcome, or at least try to address these questions. And among these classes, I highlight in this thesis the metal sulfide materials. It's basically made by a transition metal and a sulfur atom. Usually, when you have only one transition metal and one sulfur, you are talking about the binary system. It seems promising for different applications with its wide band gap, the high refractive index, and low degradation, which is suitable for solar cells, photocatalysts, mineralogies, and detector systems. But I'm not discussing on the full class, the whole classes of metal sulfide, but instead I will focus on the ZNS, basically the zinc sulfide. So zinc sulfide is a well-known material. It may crystallize in two main phases in nature, zinc blende and wurtzite. But here in this thesis, we are focused on the zinc blende arrangement that is shown in this top panel here. Specifically in the right panel, I'm highlighting the bulk lattice parameter with 5.41 angstrom and the surface lattice parameter, which will be of particular interest for us. And this is the top view of the 001 plane. Why the 001 plane? So in short, the 001 plane as well as the 111 plane display a tasked type 3 signatures, which means that we have some alternating layers of positive and negative atoms, such that a dipole moment perpendicular to the surface results. And first, these systems are not stable. Actually, to reach the equilibrium as a requirement from the thermodynamic point of view, you must compensate this dipole that arises at the surface. And for this, usually this kind of system undergoes some reconstruction. By reconstruction, I mean you usually break the translational symmetry. And this is one of the key points that we're going to explore in one of our work. And then, but I just want to introduce because it might be important in the next presentation. So overall, ZNS is a wide band gap semiconductor, as I mentioned. So if you think about the thermal energy at room temperature, which is the order of 25 MeV, this value here is pretty much higher. So that's why ZNS-based detector systems are free of thermal degradation problems. Also, you can find ZNS replete in nature. It is a common metal sulfide source. And interestingly, it was used by Rutherford several years ago in the landmark experiment that uncovered the nucleus of the atom. So I think this property explains why. However, there's some big issues on the ZNS, especially those regarding the high resistivity, the order of the petaohms. This is because ZNS is a huge insulator. It also, I mentioned about the wide band gap, but unfortunately, it is only responsive at the UV range. And if you think about the application in photocatalysis or other kind of reactivity process, ZNS, the pristine ZNS, does not display active site, so it is unfavorable for reactions. So all these issues together might impact on the both fundamental and applied research. So in the fundamental point of view, I highlight here some experiments done with XPS. So essentially, you have some photons coming to the surface and exciting your surface. So electrons ejected out toward the electron analyzer. So as your system, in the case of ZNS, is an insulator, the hole is left behind is not fully compensated because you're not there's no available magic carriers to compensate this hole. Therefore, this positive electric field that results on the surface, we're going to attract the electron that was ejected first. So this interaction will decrease its kinetic energy, and usually when you have insulator systems, you have a huge shift on your XPS spectrum. So you cannot address all the findings, all the physics behind this modifications in these materials, because you cannot disclose what is coming from a physics, what is coming from nature, a natural charging of this system. If you think about applications or applied research, let's say, you need to fulfill some requirements to split water. Therefore, if you have a limited or poor active sites, you are not able to separate water by using the sunlight. So the pristine ZNS does not seem promising for photocatalysis. So the initial question is how to overcome these challenges. A common strategy reported in the literature is the use of defect engineering. So by defect engineering, you can separate in two main classes: the intrinsic defect and extrinsic defects. By intrinsic defects, I mean the removal of a cation or anion from your system when you form the vacancy. Or otherwise, by extrinsic defect, you can just replace one of the natural source in your system by a foreign species. In this case, I'm replacing the B atom by a C atom. And then you call this as a substitutional impurity. What is the impact in electronic structure? Is when you look for for example, some acceptor defects, they might introduce acceptor levels just above the valence band, as well as if you have donor defects, it might introduce new levels close to the conduction band, and all these levels might improve both the carrier concentration and promote the recombination centers, which might allow for new emission in the visible range, and notably, it might give rise to active sites at the surface, which might turn in the first glance, a system which was not promising for the reaction. Now it become a suitable platform in this direction. So I've gathered some recent works, and I highlighted the persistent gap in the literature. In this year, there's a report on the ZNOs and S-based nanostructural materials. So they're leading with the hybrid interface, but essentially they claim that the effect might activate the surface. In this regard, I've picked up other two papers exploring the cation vacancy, which is obtained by the removal of zinc atoms in the system. And notably, they obtained, let's say, a high CO production, but they are exploring the wood side phases, and they all alpha reported that this finding is not well addressed because they just have a huge estimation from theoretical point of view. There's no experimental finding how to control the amount of zinc vacancy at the system. And also for this review, you are also looking for the CO2 reduction application. And in the same way as this previous paper, the authors state the lack of knowledge on the impacts of cation vacancy on zinc band ZNS. So that's why we're here, to try this, to try to address all these challenges. And for this, as I said for you, we combine basically experimental and theoretical tools. So, well, so we are lucky. We are working with the surface sensitive techniques here at the interface lab at CBPF. So basically, this lab features an ambient pressure system. So sometimes we use this facility, but also you can work with high pressure with normal XPS, like keeping the pressure at UHV range. We prepared the sample here in the preparation chamber when you check the cleanness, and also you obtain some lead pattern in this chamber. This chamber is assembly with this garage, and you can transfer your system in the UHV toward the analyzer, the analysis chamber, and all the system is like in vacuum, so you can control your level of impurity on your system. But this impurity is undesirable impurity actually. So we working most likely with XPS, APXPS, also with lead, and some of the collaborators in the group perform AFM and fluorescence spectra experiments, as I'm gonna show in the next slide. And here's a photo of the sample. It is a ZNS001 single crystal. It was purchased from the surface net. So it's a high purity material. So yes, you can just point to point address the modification at the surface as a function of the preparation conditions that you did. And the theoretical point of view, the ZNS surface is like a slab. It's a repeated copy of these layers. Basically, I worked with 80 ZNS layers, keeping the top, keep the bottom one fixed to mimic the bulk properties, and allowing the outermost layer to relax. Quantum espresso employ the periodic boundary conditions. Therefore, you just have this layer repeating along the X and Y direction, and you break the symmetry along the Z direction by adding a vacuum layer that avoid fictitious interaction between these layers. We run all the calculations at the Senapadi, and most likely working with the PBGGA. And for a particular case in the optical properties, as we're going to discuss next, I've performed some hybrid theory calculations, combining the description of Hatry and Fock for the exchange correlation theory. So now, as I started mentioning, there are several problems deriving from this thesis, and that might be summarized in this 5 contributions. The first third one is already done, and this other 2 is under preparation. So you discuss how the effects impact the electronic structure of ZNS and how stable is the defects on the system. Also, we try to understand the impacts on the optical response by combining experimental and theoretical calculations. And next, we move to see the reactivity of the new system. By new system, I mean a ZNS containing the defects on the surface. And finally, at the last part, we work with, let's say, real-world reaction almost that you perform at Brookhaven. So let's start with the first paper. So yes, as we discussed before, ZNS is a huge insulator. So when you have an insulator and you are measuring XPS, the charging effect impact the position of the peaks. They are shifted toward high bind energy, as explained, because the electron who is ejected left a hole behind, and this hole is not compensated. So this poor recombination hole rate implying the shift toward high bind energy. So notably, we increased the annealing temperature. So it's worth noting that all the spectra are performed at room temperature. So this mentioned temperature here is the annealing temperature before the measurements. So after several cycles of sputtering and annealing in UHV, we noted that peaks are shifted toward low binding energy. Actually, they are rising at the exact position as expected for ZNS system. So the first outcome is the charge is compensated in the system. Notably, when you compare the relative atomic concentration of sulfur and zinc 3p as a function of the annealing temperature, we know that decrease on the zinc content relative to the sulfur. So it indicates to us that the surface becomes zinc deficient. And this deficient of zinc, if you remind that ZNS001 is a polar surface, may also play a role on the arrangement of the final surface, because maybe zinc atoms are pulled off from the surface to compensate the dipole moment that you showed off initially. To address this finding, we performed some lead measurements, and of course, initially with the charging effect, there's no visible spot. But as long as you increase the temperature, we start to note that's blurry, not well resolved spots here, which becomes more resolved after the last cycle at high temperature, 1420 Kelvin. And interestingly, we can note the extra point in each row, which is picked up by, which is detected by this line profile plot here, confirming the existence of 5 points in each row. And this pattern align well with the 1/2 surface reconstruction. So essentially, when you have the ZNS system, after the treatment in UHV, zinc atoms are pulled off, and as an effect, we have the reconstruction of the surface, revealing the 1/2 pattern. So of course, as long as the zinc atoms are removed out from the surface, sulfur atoms are also removed from the surface, but zinc atoms is likely more removed than sulfur. To understand the stability of the surface from a DFT perspective, we compare the unreconstructed and reconstructed slab, both as terminated and zinc terminated plan, and which reveal that the zinc terminated plan is displayed the lower surface energy. So the lower the surface energy, the higher is the stability of the system. But interestingly, when you compare what happened at the final relaxation process, we have the zinc atoms on top, and after relaxation, they immigrate for say the inner part of the surface. So it basically means inward relaxation of zinc atoms. That's why the surface appear to be zinc deficient. So this opposite displacement of atoms of zinc and sulfur is indeed expected for type 3 surface SCNS. So indeed, the 1/2 reconstructed surface is pretty stable, and you can address this finding of addressing how the temperature imply modifications in the surface arrangement. So next, given the promising impacts on the electronic properties, we try to understand how stable is the defects on the system and what it impacts on the optical response of ZNS. Regarding the optical property modifications, an interesting result is obtained when you irradiate a sample with 405 nanometers. While the pristine sample doesn't reveal any color appearance, the UHV annealed, which means the defective sample, display a green color appearance. So again, the sample is radiated out of the vacuum chamber, and this subtle change is noticeable for us by the naked eye. So it might indicate that there's something occurring in a microscope point of view. So a collaborator of us, Luciani, carried some luminescence experiments and revealed that before annealing, there was not emission, there's no luminescence spectra. However, after the annealing process at this temperature mentioned here, we obtained two components. These components falls exactly in the visible range, which might indicate a huge enhancement of the optical response of ZNS. So now we try to modeling what is going on over this experimental finding. For this purpose, we perform some formation energy calculation. So essentially, you are evaluating the formation energy of defects as a function of the electronic chemical potential. So in this equation, I have the defective system, the pristine system, and this is the chemical potential of the atom that you remove it out. This is the charge of your system of your defect, and this is the Fermi level electronic chemical potential, as I used to call about it. And the valence band maximum usually shifted to 0, and spans from 0 to the band gap. So comparing the stability of zinc vacancies and sulfur vacancies, we can note that indeed the zinc vacancy is more stable because it's play lower formation energy. Of particular interest is this crossing point here, which is close to 0.3 eV, because this crossing point is basically the position of the Fermi energy where electrons are transitioning from the state K' to key. Which means that what kind of stability you have is a p-type or n-type. Usually, when your system took this transition close to the valence band, your system is called a p-type system. But when this transition occurs near to the conduction band, it is an n-type system. So as outcome, you can ensure that zinc vacancies are more stable than sulfur vacancies, and the system display a p-type stability. So moving to address the findings of the optical properties, we performed some hybrid theory calculations. So basically, I combined the GGA method with the correction scheme proposed by Hadri and Fock. So I mixed both the functionals, and this alpha parameter was fitted to match the experimental band gap of 3.6 eV. So all these calculations are not taking account the many body effect. So I'm working with the RPA and linear response theory, where let's say the absorption is proportional to the imaginary part of the dielectric tensor. So in this regard, initially the pristine sample revealed a single absorption peak, which is addressed to the transition from the valence band to the conduction band, and falls exactly in the 3.6 eV as expected. However, by promoting the formation of zinc vacancies, we can note visible peak around 1.8 when you have the uncharted effect, and new features, especially this one, and at 2.8 when you have the charted effects. So in generally, zinc vacancies broaden the ZNS absorption range, and of particular interest is this peak at 2.5 might explain that luminescence that you that obtained by irradiating the sample with the laser source outside the chamber, because yeah, of course, before emit, your system would absorb that light. So that light was 485 nanometers, which means around 2.5 eV. We met this result here. So the emission spectrum, on the other hand, is obtained by computing the JDOS calculation. So let's say in short, the JDOS by computing the probability of transition for a state from the valence band to the conduction band. So they take the both state. That's why it's called a joint denser of state. When I have the pristine system, we only have the single transition from the conduction band, and the electron jump back from the valence band, and the photon was emitted is only the one and at the gap, the material. However, when you have defects, as you said in the introduction part, it might introduce shallow levels, and these shallow levels might act as recombination centers. And instead of recombine directly on the valence band, the electron can jump back to the shallow levels, and then photon is emission with energy E prime, who is the difference between the gap and in these shallow levels. Noticeably, we obtained good correspondence between our experimental finding and the theoretical result. We obtained two compounds here with the charted zinc defects around 1.9 and 2.2 eV. And indeed, the cation vacancies are responsible for new emission in the visible range, as explained, as suggested by experimental features and obtained here and the theoretical point of view. So the takeaway message after these two parts is zinc vacancies can improve the ZNS conductivity And zinc vacants enhance the optical response. So especially the charge vacants, which may coexist with the neutral charge effect, are responsible to drive all this modification reported here. So now we start our seeking for reactivity on ZNS. So we are gonna work with the oxidation of ZNS single crystal, and we most likely try to understand how does the oxygen atoms can enter in the lattice and how it changed the electronic structure of the former CNS system. So here's the XPS analysis. So initially, this is the survey analysis revealing the features which belong to sulfur ZNS, and like zinc 2p, sulfur 2s, and sulfur 2p. But also it display oxygen features, especially after the 5 cycles of oxidation. We can note a huge peak here of the oxygen atoms, and it's still the presence of the sulfur features, which might indicate the formation of a hybrid interface of ZNO and ZNS. By analyzing the oxygen evolution, we can disclose this peak in 2 components. The most likely the 530 is like zinc bind to oxygen, and the other one belongs to a native peak. It's not defined in the literature, but it's most likely like water in the chamber, or around the lattice, surrounding the oxygen sites. But what important most here is the relative concentration again of sulfur and zinc. So as you said, we start with a defective surface, and this defective surface allows for the oxygen reaction takes place. As long as you start the oxidation, the sulfur content decrease, but it's not decrease like you are not inserting more zinc in the system. Instead, we are putting oxygen atoms into the lattice. That's why the signal of sulfur is mitigated. Interestingly, when you compare the zinc signal against the oxygen signal, we can note that at the last cycle, it reached almost a half of each odor, which means that the half of the ZNS surface is covered by ZNO. So basically, we by carrying this experiment as this condition here you have here, ZNS is converted in the hybrid ZNO ZNS system. So you can try to figure out what happened in an electronic point of view by computing the Korolev analysis. So here's the ZNO sample. It's a reference sample. It's ZNO 0001. This is the former ZNS, let's say the doped ZNS system, but before the reactivity. And this is the ZNO ZNS interface after the last cycle. And we can disclose this peak now into 2 components. And now we have the ZNS feature and the ZNO feature. And interestingly, if you know the sulfur behavior, we can note a shift toward low binding energy after the formation of the ZNO ZNS interface. The shift toward low binding energy always suggests to us a bending-like effect, which might take place during the introduction of oxygen into the lattice. Also, if you look for the OG lines, we can note that after the oxidation of the NS, so you have this shape of the OG peak. This shape is converted in a ZNO-like shape, because if you compare the reference sample, the ZNO 0001 is quite close to each other. So indeed, we are converting the ZNS surface into a hybrid ZNO-ZNS interface. So we can question ourselves about what kind of alignment you have. Is type 1, type 2, or type 3, because when you have the heterostructure, we have several possibilities. In this case, as ZNO and ZNS have similar band edges, a type 2 arrangement is expected. So for modeling this, we compare the valence band of the materials, both the reference sample here. So we're revealing the valence band maximum at 3.1 eV, the ZNS before the oxidation, at 2.7 eV. And then we compare what happened after the full oxidation of the ZNS, and we noted a decrease, a shift toward low band energy as expected with the band bending. The shift toward 2.4 EV. In addition, we can note the suppression of this component A prime here. So A prime is typically, in this case of ZNS, is like most likely sulfur 3p states, and the sulfur 3p state at the surface are mitigated, but of course it might be well resolved from UPS measurement instead of XPS, but for the sake of simplicity, it is not shown in this presentation. A recent paper has taught us how to model the offset when you have a hybrid interface. So here's the rules. You must choose, if you have the system A, now overlay A over substrate B, you have to choose the signal coming from the overlay here. So you choose that oxygen 1s as the peak, and you measure the distance between the score level peak and the valence band maximum as you computed before. So similar for the substrate signal. So for the substrate signal, we chose the zinc 2p and compute the distance between the zinc 2p peak and the valence band maximum when you have only the ZNS. And then finally, we compare the relative distance between the overlay feature and the core level feature when you have the hybrid system. So that's why you have the AB core, A core, and the system A over B. So coupling all together these parameters, we can evaluating let's say the valence band and conduction band offset. But first, I would like to highlight this method reported a couple of years ago that taught us how to estimate the band gap from XPS. It's important to do this because, of course, you can use literature results to use your equation to estimate the band gap and then compute the CBO, the conduction band offset. But it will be better if you can do by yourself with your own sample, and that's what you can reach by following the description here. So essentially, you have several loss mechanisms during the photo emission, and the lower in energy is those that represent the transition from the valence band to the conduction band, which is exactly the band gap of material. Usually the signal is poor, so to see these features, we might increase the acquisition time, the number of steps used in the process, and then we are able to note the onset peak here when you highlight the zero level, and then fix it let's say the center of the peak of each case. We just need to compute the relative distance between the zero level and the fixed the center of the peak. So computing these two difference, we obtain for the ZNS 3.77, which is pretty close to the 3.6, and 3.4 for ZNO, which is close to the reported 3.3, 3.2 EV. And then computing this equation for the valence band offset, you can now use the band gap estimated from XPS to compute the conduction band offset. Overall, these parameters and these values is reported in the panel B. So initially we have a ZNO with a lower, with a less negative conduction band minimum, in a high positive the valence band maximum, and which be aligned to a ZNS system. And this alignment promotes in the interface the flow of electrons and holes, which might give rise to a built-in electric field, which is suitable for the charge separation. So basically, we're promoting the formation of a potential platform for efficient charge separation, which might be useful for water splitting process, hydrogen evolution reaction, and oxygen evolution reaction. So the takeaway message for this part is this one. We can just perform the in situ oxidation of the ZNS system, just exposing your ZNS to oxygen atmosphere around 10-5 millibar. And interestingly, the system, the resultant system is impurity free, so there's no contamination from carbon, nitrogen, or other species. And this hybrid interface displays suitable levels for a wide range of applications, especially in the most likely linked to photocatalysis. So Also, we highlight here that oxygen atoms are readily absorbed on the defective ZNS surface. This is particular highlight because now we're gonna explore others oxygen-containing molecules interact with the doped ZNS surface as you did before. So this final part was carried at Brookhaven National Laboratory under supervision of Professor Anibo. And today I'm gonna just highlight the main outputs that you're obtaining and what we are figuring out for the manuscript that is under preparation. Just a minute. So, so starting, we exposed the ZNS sample to CO2 pressure of 0.55 millibar. And at the same time, we heated up the system at different temperatures. So this is the operando condition of the system. And we note that at 373K, there's no satellite peak on the left, but curiously, when you increase the temperature, these peaks start to rise and become broader at 573K. Usually from the literature, this peak assigned for the CO2 fingerprint. So this result might indicate to us that the reaction initiates at 473K, and comparing the contribution for the area of each peak in the scenario, we know that at 573K, this component regarding related to the CO2 species are most likely higher than this at 473. So at 573K, you can say the reaction seems more efficient. Gradually, when you move back to wet V, so the gas, you pump down the gas, you wait for the room temperature, turn off the laser, which is hit the system. We still noting this small contribution, but now in this panel, I've performed a different pressure just to comparing the dependence on the coverage, because I've exposed it to 0.55. Now I've repeated the system at the same temperature for 573K to compare the whole of the coverage on the CO2 interaction with ZNS. And we note here that although we're having a slight increase of the CO2 fingerprint, we also obtained a huge contribution for water molecules like carbon bind to oxygen and hydrogen. So this is not suitable for us. So that's why you can say you can work with low pressure. Apparently, there's no dependence on the coverage for the CO2 reaction takes place. And so henceforth, we're gonna work with 0.1 millibar and at 573K as your target pressure and temperature respectively. So we can do let's say, the UHV spectrum before and after analysis to highlight the modifications. So when we look for zinc 2P or sulfur 2P, we note a slight shift toward low binding energy. So it is quite interesting because it reminds us what you obtained for the oxidation of ZNS. So basically, the CO2 might be used to oxidize the ZNS surface, but note that this oxidation is not that higher than before, even exposing the system to, let's say, higher oxygen content. But of course, this oxygen in the CO2 molecule is not free to move, and apparently it's not being dissociated. Interestingly, the oxygen peak revealed to us after UHV two components, the oxygen to bind to metal, and the other one belong to oxygen bind to hydrogen, as you said before. And here's the highlight comparing the experiment before the exposure and after the exposure when the satellite peak is still there. Which might indicate that's non-reversible process of non-dissociative CO2 reduction adsorption on ZNS. So now we try to figure out these findings from a DFT perspective. For this, we compute the adsorption energy as shown here. Basically, you have this lab containing CO2 and this lab without the CO2, and the CO2 molecule optimized alone in a cubic box. And if you look for the adsorption energy, we can see that indeed, when you have zinc defects marked in this slashed rectangle, display a lower dissociation energy. So probably the defective ZNS surface is responsible for, let's say, interacting with the CO2 molecule. We highlight here that, as expected, the CO2 is not dissociating, and also is coming close to this vacant center and slightly bend its orientation, but not getting any kind of dissociation products at the surface. So it's most likely a weak physical mechanism of interaction of CO2 and the ZNS surface. As you said, oxygen atoms readily adsorb on the ZNS, especially those containing zinc vacancies. And we compare this outcome by evaluating what happened when you have the pristine surface and the doped surface exposed to oxygen. So the pristine surface display an endothermic process, which means it's huge unfavorable in the terms of thermal stability. But on the other hand, the doped system isothermic process, and also the oxygen atoms is bounded on the ZNS surface nearby the defective sites. So it's a signal from the chemsorption taking place on the ZNS. So this is also important to highlight. The distance between these oxygen atoms has increased. It's typically 1.22 angstrom, and after the association here is like 1.4. And as long as you increase the bond length, it might indicate that the system, we're gonna dissociate each other. So as DFT is under 0 Kelvin, we are not able to see this fully dissociation, but it might indicate that if either thermal excitation or interaction with other molecule might take the system to dissociate and be used for another reaction. So that's why you would move it for the last part when you try to take insight from the CO oxidation of ZNS surface by combining CO and oxygen. So we are looking for toward CO oxidation. In the left panel here, we have the UHV spectra at room temperature, but comparing before and after effect, the stoichiometric reaction of CO and oxygen. So initially, we have this peak at it's not marked here, I don't know why, but anyway, it's around 1022.8, and this peak is slightly shifted toward low bind energy. 1022.4 is expected. And the oxygen atoms reveal to us three new components. This is the oxygen bind to metal, this oxygen bind to water, and this is the oxygen, let's say, like make a dative bond according to the literature results, which means that an oxygen that belongs to the lattice. That's why I claim this OL, but it's also surrounded by other water atoms and, let's say, the environment atoms. But curiously, at this scenario, we are not able to see the fingerprint related with the CO2. Of course, if you are combining oxygen and CO, one product that you are expecting is the CO2 formation, but it do not arise, at least comparing this before and after. We have the in situ data, but again, for the sake of simplicity, you are not showing here. And the right panel, on the other hand, by increasing the oxygen pressure, now we have the right stoichiometry to get the CO oxidation. We just use the same oxidized ZNS surface, as you can note here. And now we have two interesting features. First, the oxygen lattice content is decreased. And now we can you can obtain the CO2 fingerprint. There's a solid peak on the left. So in addition to the CO2 feature, we might suppose the place where the CO is sticking on. So this experiment is suggesting to us a core social mechanism where the CO is being anchoring on the oxygen side and then promoting the separation of the oxygen at the surface, giving rise to other CO2 molecule. To understand this finding from a theoretical point of view, we try to model the system by exposing the oxidized DNS surface to a CO environment. So here's the step of the reactions. So essentially, when we have the oxidized system and the CO gas phase, the next step is the CO gas phase comes close to this older oxygen side. So there's a core dissociation of CO over the oxygen atoms. Next, this older 2 oxygen is dissociated, resulting in a CO2 molecule on top, pointing toward the zinc vacant side. And the final cycle, this CO2 molecule resulted from the dissociation of step 3, leave the surface and behaves likely CO2, just bending its orientation and interacting via physical mechanism with the still oxidized DNS surface. So in general, you are showing here the social mechanism via the core dissociation of CO or over oxygen sites. So let's try to summarize the outcome of this part. So essentially, when you have the CO2 on pristine and doped DNS, you are only taking interaction of the ZNO of the CO2 with the defective DNS surface. Also, oxygen molecule readily can absorb on the defective DNS, as you saw. And this is of particular interest because this oxidization of the DNS surface might help us to trapping the CO and then get the CO oxidation via the core dissociation mechanism, as highlighted here. So I'm coming to conclude my presentation. So I provide the general remarks. In short, we work with the DNS and we apply a defect engineering like to promote the meeting of real-world challenges and the solid-state physics. And then, as a result, we were able to see the modifications on electronic properties, the optical response. We were able to promote new interface design, which is promising for several photochemical applications. And also, we were able to obtain a surface which seems more reactive. So we are on the way to obtain several reactions on the defective DNS surface. So concluding, I would like I'm so thankful for my family. This thesis is dedicated to them. It is one of my father who passed away 3 years ago. So he was a tough period in the life, but fortunately, hopefully, all the support of my family as well as of my friends, both from CBPF and Brookhaven, has helped me to keep going and be resilient. And then we overcome the challenge. I'm not here alone. All your people support me, and I'm so grateful for all the help during the way. I'm sorry if I forgot some names that I'm not mentioning here, but all you guys are so important for me. So I'll give back the word to the committee, and I'm open to question right now.
Great. Thank you, Pablo, for your presentation right on time. I did a sign here of 5 minutes, but I guess you didn't needed this because you were exactly on time here. So to continue now our evaluation here, I would like to try to some order here of distance from the project itself. So me and Aníbal for sure going to be the last ones, but I would like to start with Professor Renata Simão, if possible. Can you hear me?
Yeah, for sure.
Renata? Yeah, great.
Yeah.
Yeah. So please take your time on your evaluation question and so on, right?
Thank you very much for the invitation of being here now and participate in this thesis. Pablo, you really did a good job in talking. It is really a very interesting topic too. It's really, really interesting. I think that defective engineering is really very important, and it's important to do it in the right way and really clean surfaces and everything. So I'm really very happy with your work and the work of Stavali. So I I I congratulate all of you for that. So I I I have some points to discuss, I think, and also to comment on your writing more than on your talking.
I agree.
So, so when and I think you should do better now on your writing, just because
I had more time actually.
really have a very huge amount of work. It's really impressive how much you worked and how good you did. So please, I think you should improve your text for that, for showing this in an easier way. So that's my main point now. So I will start with your chapter 2, the
Sure.
XPS.
I'm
Why
sorry.
did you write all you did about XPS? Because
Okay.
the important points that really makes a difference, like charge compensation and so, you didn't talk about it in your XPS chapter. So I would say, throw it away or do it right. You may choose.
Yeah. First of all, I apologize because I forgot to mention about the charging effect on ZNS, on the XPS system. I just explained the presentation because I also noted the lack of information, the manuscript in the thesis document. But for the XPS, I just want to highlight let's say the key points, the features, the overall features of XPS, similar as I did for the DFT. If you noted, the PBE alpha methodology is coming from the appendix, is not present in the former part, the core part of the thesis. But yeah, I totally agree with you. I had to include this a new section, a small section mentioning about charging effect because I thought I'm mentioning about several effects like the relevance to use monochromatic source, like what more? The all the process regarding the XPS, short introduction about what happening when you have what I forgot what it is better if I open the thesis, I guess. But anyway, the charging
Okay.
effects, the charging effect is not
You
mentioned.
should improve. I think this is the best part. So
Yeah.
what I
What
would
do you?
do
Pablo,
if I was
Pablo,
you, I would put it in the end of the thesis, like an appendix also,
Yeah.
and then make it complete. Also with UPS and all these things, because you used it a lot for calculating band gaps and differences in energy and so you should put it more or less all together at the end of the thesis. And I think it would be better that way. I don't know.
Okay, just a question on that, Renata. Are you suggesting to include a new section in the XPS chapter, or just move all the XPS part away through the
Yeah, move
appendix?
all the XPS part away, I would say.
Okay,
I
okay,
think it's just a suggestion. It's just the way I felt when I was reading, you know.
perfect, catch it.
Oh, there is some details on the writing, but I will not comment on them.
You can share with me
Um,
later.
yeah, I do.
Perfect,
And
appreciate it.
yeah, and then when you move to chapter 3, you start just saying again the same motivation you did in the introduction. I know you are just reporting your papers, but I think you should be careful of that.
Okay. Actually, I try to extend my motivation the chapter 3 because the former text there was a lack of motivation. I was straight for the results, and then the last time you complain about this, so okay, this So this chapter is dedicated to Renata. But okay, I appreciate your point anyway.
Yeah, but you know,
Yeah.
it's you did it very well in your talk. You
Okay, thank you.
just think about the way you presented everything in your talk, and then try to take this to your text too. Yeah, just follow your slides. I think it's a good path.
Okay.
Like in page 19, in your slide 4, you can show the slide, please.
Hmm?
No, yeah, this one. This image where you show the red and blue balls, it's not really explaining in the text. Or I think you should include the first the upper image,
Okay,
the
okay, sorry.
image on
The
the
Zigbee
upper.
arrangement.
Yeah, I
Okay.
think if you include this, it can be better. And even the explanation on this balls joined together, I don't know where the surface is. There's no sign where the surface is. You say, okay, you have a net dipole moment, but where is the surface?
Yeah, it's like a top view of the surface actually.
Yeah.
Yeah, it's not what I explained it. Perfect. It's likely a top view as similar as I did in the Zigbee arrangement on the right panel on top. But of course, you're 100% right. I go for it. Definitely.
So yeah, there's a lot of comments on the text, but then I think you can see.
Mhm.
And let me see. And I think it's great what you did. You know, you joined together the experimental results together with the DFT and all the calculations. This was really great. And I think you um, you are evolving enough for being the researcher that Brazil must have. And I hope you stay here.
Yeah, let's see what happens.
Although we don't have sometimes much place, but I think this is really something that we as older researchers, I think we should um, incentivize, guarantee that we have people like you formed in the way you did better. Yeah, I think we should have places for people like you, because this is really physics, and
I
I
appreciate
think
it.
you're really
Yeah,
in,
I think
in a very good shape.
yeah, I think science is a bridge between experiment and theory. So you cannot be like mocking all the theoretical point, and also you cannot avoid to understand the what is happening behind the scenes, you know? Like why not? The XPS spectra is showing this? What is happening in the let's say the game in the deep level, you know. So I think all the solid state physics must go for the experimental and theoretical tools. So I totally agree with you.
Yeah, this is true. So and then there is something that you said, you wrote somewhere, I don't know where, that you use more than one XPS. Yeah, you did sometimes you did all your measurement in this one, and sometimes in the usual one.
Yeah,
Can
yeah.
you talk a
Uh,
little bit about this and explain me?
Yeah, in short, this XPS capability is a near ambient pressure, so you have a different pumping system. So it allows to expose your sample to ambient pressure, near ambient pressure condition, though keeping your whole system in vacuum. So when you're not performing ambient pressure experiments, we are always working under UHV. So I've performed all the way with V experiments. So that's, I mean, the traditional XPS. And also I've exposed the sample to ambient condition. That's what I mean about near ambient pressure. But the result reporting in this thesis is regarding the near ambient pressure experiments were performed at Brookhaven, but I didn't have the picture of the system, but it's quite similar, of course. There's a different pumping.
I
There's a
thought you used the other equipment, the one from the old equipment from CBPS. No?
no, I've used it, but the result that you saw and you read are derived from the outcomes from my period at Brookhaven.
Okay. Okay. And then when you started the second part,
Can I comment on this? So this,
uh-huh.
at the end, whatever I comment during my supervision, you know that the student do whatever they want, right? But that's one point. In the experimental session, it's not full clear which equipment used for each thing. And if we have to use something to describe the NAP express, I'm pretty sure that Hannibal is eager to share pictures of the equipment there, and you include this because whatever what we are doing, we should not like misleading the reader, and then it should be full clear that there's and it's not because it's not has not to do to say thank you for the equipment itself, but it's actually to make clear which kind of setup the person was using from one
Yeah,
experiment
that's the
and the other,
point.
because you want to reproduce, you want to like know, oh, I know that this kind of experiment is not possible in this equipment, so should be a picture that's accurate, and this is something that we have to amend in the final text that make clear that this experiment, this chapter 1 and 3 was this equipment at these conditions. The other equipment is another equipment. Also to mention the resolution. Maybe if it's the same
Yeah, that's
company,
it.
the resolution, everything, because
Yeah,
whatever is specs is not the same. We should like put it in
yeah,
the
yeah.
same one.
Yeah, totally agree. I've just mentioned in the text that the system are quite similar, but the difference is the way that you heat the sample out. Here's the ceramic heating. At Aníbal's lab at Brookhaven, you have the laser system to heat the sample. But of course, in the final version of my thesis, I will improve the description of all the chapters. I don't know if I include before the results or I insert on the
You
methodology
didn't.
chapter.
Yeah.
No,
I think
I
that
will
you
do it.
should
I will
have
do it.
a very
No,
small paragraph on experimental in each chapter, very small, just to locate the reader, yeah? But because
yes.
as there are so much parameters and all this thing that you did here or there, and I think you should do it because then it will be easier. Like comparing figure 3.2, where you have the different heatings of your surface, with the figure or the next chapter where you put the image, the 4.2 XPS spectra. I think then you are near that 150, and then it's a little bit different, and why you use one or the other. I think this is the point mainly, to try to compare the results, or to say if they are comparable or not, and this is my point.
I'll be attending point to point of your suggestion. Yeah, I totally
Yeah.
agree with you. Yeah, that's
Now,
perfect.
Pablo, if you have the printed version, please take note because we're not here in the same room, but all you otherwise you take note of this on the
I'm taking
PDF.
notes. I'm taking notes.
Okay.
Yeah, for sure.
No, because in page 12 is exactly this point that she's arising, because that's some of the confusion. Like in page 12, when you describe the equipment, at the end you say, oh, the equipment there was similar to this one, but I think we should not keep like this.
Yeah. It was a
We should
weird way to
separate it.
describe. Yeah,
Okay.
for sure.
All right.
Page 12. Okay. Thank you.
And I like very much this oxidation of the surface. Because if you look at XPS only, you will see the sulfur. Yeah, this one. you will, yeah, this one. You will see this, the zinc sulfide peak and the zinc oxide peak and the XPS. But then when you look at OG, okay, they are broader or so, but I don't think it's just the sum of one and the other.
It's not really. I mean,
Not
this is
really.
the, yeah, because the ZNO, I think this ZNO single crystal is a reference sample, and then I exposed the ZNS for a full oxidation, and then we completely changed the shape of the OG lines. So it's most likely converting to a ZNO. So you are changing the oxidation
Not
state.
really. Not really, ZNO.
It is
You don't
similar to
have
ZNO.
two peaks. You have
No, perfect. It's not ZNO.
you
It
have
is
a
still being
really broad peak, like
it is still being
you
ZNS,
have
but
a
no, no.
different stuff, like you see in UPS, you know?
Yeah, I mean, it's remind me the ZNO peak is not a ZNO OG peak. It is a
Yeah,
hybrid of ZNO and ZNS because I have a hybrid system. But I'm not saying I have two components like one for ZNO, other for ZNS, and so on and so forth. Because this signature here is most likely due the core level sensitive of zinc 2P levels. You know,
yeah,
we are working with a thinner layer of CNO actually. I've estimated the thickness. I think is around 4 nanometers, so not that higher.
yeah. But when you look at this, the valence band, you see also, I think that the mixed is not really one or the other.
Yeah, but it is well resolved by UPS rather than XPS actually. You know,
Yeah, and then
it
go a little bit. Change
back
change the slides, please.
this one.
Another one. Your model, the model
Yes,
that you
here.
made.
Okay,
Yeah,
there you
this one.
go.
Again, the model, the ball model,
Oh, Foxer.
the ball. As bolinhas em cima do. This one. Yeah. And when you look at it, you say that the interface is sharp. So you have ZNS and ZNO. Do you think it's really sharp? Do you think, is there a mixture on both species? I think the oxide does mix with the or goes into the zinc sulfide.
I believe that mechanism behind the oxidation is like most likely some sulfur atoms that pull it off on the surface and the oxidation takes place and then it will be bound to the zinc atoms. But the growth mechanism is likely island to layer transition. So it's not like almost fully covering the ZNS, but just making a small interface. A colleague of mine, Igor, has performed a FEM image. I've presented in the thesis text, but I prefer to not discuss here in the presentation. But there's like several signatures of the island growth mode. So there's a mismatch between the ZNOs and SNO. So I'm not expecting a perfect staking of ZNO over ZNS actually. So
Yeah, I do not too. I think you should decrease the exposure of the surface to try to get what is really the initial, this initial layer that is what's happening. Okay.
Perfect. That'd be great.
And the idea of using first CO2, okay, because CO2 is a really a point in the literature, but then to explore what happens with CO, this is very interesting. I like it very much. Oh, this approach that you did. So I think
Yes,
I already took my time.
Okay, appreciate it.
And
Appreciate
I
your
think,
time. Appreciate the evaluation.
and I will send you the modifications on the text and things
Please.
that I
Appreciate
just
it.
thought when I was reading. And I congratulate you for for your thesis and for your presentation. And I hope you can do really a good job now in the text, because you
Yes.
deserve it.
Yes, I go
That's it.
fully feel all your points that you raised it up, and I appreciate your time and all your comments and suggestions.
Thank you very much. Thank you, Fernando, for inviting me and letting me give my opinion on that. Thank you.
Thank you, Renata, very much for your comments. And then I'm pretty sure that Pablo is going to address all your comments. So now I would suggest that we move to the theoretician in the committee, that we get a different point of view. So if Eduardo Cisternas, yeah, great, can take over, I would appreciate. So thank you for participating as well, Eduardo.
Okay. Thank you, Pablo. Thank you, Fernando, for the invitation. It's really a nice work. It's really impressive, the amount of work that you did. So congratulations. Congratulations.
Thank you, Sita.
In any case, I have some question. As Fernando said, I will concentrate on the theoretical part. And I would like that you explain me in slide number 7. I saw that you added some extra atoms in the bottom of the theoretical model. Could you explain me why did you use that?
Yeah. In short, here's our hydrogen atoms just to passivate in the surface to avoid any kind of fictitious state contribution to the band structure in this sort of state, and also avoiding, because when you have the surface, the top layer are uncoordinated, but the bottom one is mimic the bulk, so it cannot be uncoordinated. So that's why I used to passivate it with hydrogen on the bottom.
Okay. Thank you. In the slide number 15, it's not clear for me. 15, yeah. In the text, you talk about the joint density of states, but
Yes.
I don't know if you use that part to obtain this absorption spectra or
Not
not.
at all. Not at all. I think I didn't include on the experimental method, but in short, I just compute the dielectric tensor, and then I took considering the absorption is the same through all direction. So computing the model of the average of the dielectric tensor around X, Y, and Z direction, I obtained this absorption spectra, because in this approximation, the absorption spectra is proportional to the imaginary part of the dielectric tensor.
Yeah. Okay, great. And so you obtain that in the case of vacancy, the zinc vacancy, with
Yes,
a
yes,
charge
really,
-1,
yes,
we obtain a important absorption peak in the visible spectrum. No?
yes, definitely.
Okay, good. And in slide number 14, okay, 14, sorry.
14?
Yeah, 14.
I
No,
think
no,
I,
no.
40,
14.
you mean? 14, I'm sorry.
Sorry.
Yes, in this one.
Yeah. Okay, you in the right part, you have a graph of the formation energy versus the potential, the chemical
From the level
potential.
of the chemical potential, yes, definitely.
Yeah, but in your equation, you use also a chemical potential that you mentioned, like UX or something.
Yes. I mean, this chemical potential here
Yeah,
accounts this chemical potential here accounts for the atom that I move it out from the system. So to
yeah,
compute this part, I first calculate the total energy of the existing system, and then I isolated let's say if I remove the zinc atom, I just put the chemical here it's a sulfur-rich scenario. I forgot to mention it. So in a sulfur-rich scenario, the chemical potential of zinc will be like the difference of the total energy of ZNS minus the 1.5 the total energy of a sulfur molecule in a isolated cubic box.
Yeah.
So it is.
And in this case, this parameter is
It's
fixed.
fixed. Yes,
Okay.
definitely it is. Yes.
Okay. Okay. Good. All right. Also in slide 12, I think, yeah, there. Do you talk about the surface reconstruction of the single, sorry, the
Mhm.
zinc surface?
Mhm.
Yeah. Could you explain me if you put these two cases in a different starting sequence, or or how did you did that?
Oh, this calculation was done by Professor Corina Orville from
Yeah.
UFSCar. I've just reproduced the calculation, and my point, we got the same result. I can say to you, we performed the same mechanism. So usually we have the estimated plan and then compute the total energy, the surface energy. We have the estimated plan and then compute the surface energy, and then by looking which one is the most stable, we performed the final relaxation structure in this reconstructed surface just to monitoring what happened with the outer layers of zinc and sulfur, So basically, essentially, you have two different calculations, and for the high stable one, we did the full relaxation of atoms.
Good, good. I understand. This is clear for me now. Maybe my last question is about the CO2 absorption. I don't remember the slide number.
Yes, there is slide. There's no number in the slide actually. I'm sorry.
Yeah.
Uh, it's it, it,
Oh,
it,
yeah.
it's pretend to be 24.
Yeah. Okay. That's okay.
Okay.
In your calculation, you obtain your absorption energy in this case.
Yes. Yeah.
Yeah. Um, please explain me a little bit more. How did you obtain that number? I mean, you
Mhm.
start from some distance with the molecule, and then you relax the system, or how
Yeah.
did you do that?
So first of all, I've optimized my ZNS surface itself,
Mhm.
both defective free and defective ZNS, and I've optimized the CO2 molecule, put in a box and isolated CO2, just to computing the bond length between the carbon oxygen atoms and also the CO2 angle. And then I just coupling all together in a slab. But like I was exposing the gas phase of CO2, so it is free to move all the way. So it is not attached to the ZNS surface, but is slightly close to the top layer atom. And then I allow all these first layers and the molecule itself to relax. And the final configuration is resulting by minimizing the Hellman-Feynman theorem,
Okay,
So,
okay. On how much time did you
okay,
take?
with van der Waals corrections, it took like 1 month to run all the calculations because
Ah,
there's a limited step. I think
yeah,
you're limited to 50 steps,
yeah.
so it's not straightforward. So we have the first cycle, 50
Mhm.
steps,
Yeah.
start again, start mode, and so on and so forth until you get the conversion. It took me like 1 month, I guess.
Okay. It's just to have an idea because it's very interesting that you did what you did.
Yeah, appreciate it.
Yeah, this was my last question. I congratulate you for your work and congratulate Fernando. Yeah, I know that he was guiding you constantly.
Yeah.
And thank you again for the invitation.
Thank you, Eduardo, for your comments. Thank you for your questions. And also, I acknowledge you already sent your comment in your thesis, and
Oh, yeah.
I will attend all your topics that you raised in my PDF file. Appreciate
Okay.
it.
Okay. Thank you.
Great. Thank you, Eduardo, for taking your time to read the thesis. Now can we move to Professor Tulio Rocha from CNP? Great, Tulio, thank you.
Yeah. Okay, thank you very much for the invitation. I learned a lot reading the thesis. Congratulations for the work, Pablo. Your presentation was very good as well. I have comments very similar to Renata. You have a wealth of results. It's very well analyzed, and I really would like to congratulate you for that. And especially the fact that you are always trying to combine theory to support your claims, right? You're always trying to, you have very solid experimental evidence. You always try to combine with theory and to extract information that you combine both results. And this is really good. But I agree a lot with Renata that the quality of your manuscript does not reflect the quality of your results or the quality of your presentation. You have to improve that.
Yeah.
And it's important to do that for other people that will continue this work, other people in the group, or for the many other people that might consult your thesis as a reference material. So I think you should spend some time trying to improve that.
I totally agree.
The storytelling in your presentation is much better than in the thesis, and I think I understand why you try to include parts of motivation throughout the text, but for the reader, it's a little bit redundant and it's back and forth. So you should think about the reader when you write the thesis. And I have some comments before about the manuscript and the form, and later on I have some comments about the results. So continue this with the form of the manuscript. I think review the English as well. There are some things that you repeat a lot, like ending systems, some very long phrases. So just review the English. The quality of the figures, I think, is much better in your manuscripts that in the archive and the presentation than they are in the thesis. I think the low resolution or something that the quality of the figures are not good there.
Yeah, it's the extension file, I guess. I think most of them was not PDF file. It was like PNG, and I lost some resolution. I will double check.
The figure captions as well. I think from the part that you have published results is very good, but for the first half of the thesis is very short, the caption. It should be more informative. Like if you read the figures, we should be able to understand the whole thesis without going to the details on the text. Like captions plus figure should tell a story in itself. And the first half is not like that. The second half is much better.
Yeah, totally agree.
And similar things for references. There are some points you put a lot of references, but especially in this contextualization, you put a lot of information and some claims that are not supported by references. And all of these are indicated in the manuscript. I'm just commenting here that you do not...
Okay, it'd be great if you can send me later.
Yes, yeah, definitely. And one thing, just my last point, is this separation between what is context and motivation, what is methods, what is preparation, and what's results. I think this in your text, it's sometimes you mix these things, right?
Mm-hmm.
And I think it's better to separate. I know there are different writing styles, but separation is always better because your manuscript might have different roles. For instance, if I want to reproduce your results, I just want to take your thesis, give it to my student, and tell him, here is a zinc sulfide single crystal, reproduce this. I want this defect to study here at my beamline. it's very hard to do that because I have to read the whole thesis to find how you prepare the surfaces. So you
Yes.
don't have like a preparation, or you know what I mean?
It is my fault. It's totally my fault. My advisor has requested me about this shape of thesis, but I prefer to just keep in the methodology close to the results section such that the reader can see the results and then come back a little bit and then see the preparations. But I think I can extend the discussion on the preparation, or just split up in a new section when I include all the way the experimental methodology that I took. But yeah, it was like a style thing that I chose it, and of course I will correct it.
I think it's more like if your thesis work as an archival of information, is easier for people to retrieve the information if it's separated in parts. So if I want to read your thesis to understand the motivation for zinc sulfides and the system, I go to the introduction. I don't have to skip several chapters. Or if I just want the results. I know the motivation, I know your methods. Then I'm reading the results, and there's a lot of text in between.
Agree? Yes. Okay, I can prove it.
You can make short mentions if you want to remind the people that some result depends on the preparation or the method. You make a short sentence or a short paragraph explaining, and you refer to the chapter or to the appendix.
Mm-hmm.
But I think it's something. And another thing more general that I missed is error analysis.
Yeah, I think
You
it is
extract a lot of numbers from your
Yes.
thesis, and many of them come from assigning binding energies or areas or leading edges that you extrapolate lines, and they are all sensitive to errors, experimental errors. And then you extract information from combining differences between these numbers, but we don't know whether these are above the error bars or they're below the error bars. Are they reliable? From the
That's true.
quality of your data, they are clearly above the error bars. But this should you show the strength of your results, that you
Yes.
make claims that are above the error bars.
Okay, I totally agree. I will do that, definitely. I did only for when I discussing the relative concentration of sulfur and zinc. I don't know if I mentioned
exactly.
that. Yes, I do the same. I have the methodology for all the comparison, and yeah, I can do it in the same way for the binding energies and for the concentration and so on and so forth, for sure.
Yeah, especially for that models, the band alignment models.
Yeah,
These
yeah,
are
totally.
tough to do, and you did a really nice method in the end. Yes. So you combined a lot of information, and you can propose a band alignment model that is based on solid experimental evidences. This is quite strong.
Yes, I agree. I
So
do
it's
it.
not. This is not a cartoon. That's what most people plot this.
Yes.
It's
It's a building diagram, yes.
it's built from experimental evidence.
Yes, experimental guide diagram. Yes.
Exactly, and you should emphasize that.
Perfect.
Then I have some questions. I'll go from the different topics. From the zinc blend, from the part of the first topic, the zinc sulfide zinc blend. Yes,
Okay.
that was in.
Yes.
I also missed the surface image of the surface reconstruction and the structure. This is not your thesis. This should be in the thesis.
Which one? The lead pattern?
This figure on the right hand side.
Oh, really? Oh, okay. The
It's
DFT.
nothing.
Okay.
Like you mentioned, it's 1x2 reconstruction. What is 1x2 reconstruction in real space, not in the LD diffraction pattern?
Definitely. Yeah.
You should put and to give
So yes, chapter, and I think it's 4. Include the DFT theory. Mhm.
And it can be a drawing. You don't need a DFT. But
No,
when you
yeah,
assign to a 2x1,
that will be guide
what's
the
the
reader.
structure in real space?
Yeah, definitely that will be guide the reader to the what does 1x2 means. I
One
had
by
that
two, yeah, exactly.
Mhm.
In this sense, it's not clear the point, the experimental evidence that you have is that you have more the sulfur to zinc ratio changes, right?
Yes.
It's not clear whether you have more zinc or less sulfur, right?
From the simulation, the core idea is we have like the zinc atoms moving inward to the surface, and that's why you are conferring the sulfur rate, apparently the sulfur rate configuration of the ZNS, you know. And in this paper, in this first paper, we are not promoting like a full zinc vacance formation or sulfur vacance formation as you did in the second paper. We are just most likely understand the mechanism, because the main outcome here is how does the surface can compensate the dipole, and also how does the preparation condition impacts on the electronic configuration, the electronic response, and the surface arrangement after the what you saw, which means like which be like what happened when you remove it out some zinc atoms, preferentially than sulfur. So this simulation is just teaching us that the surface behaves like as expected, a type 3 Tasker surface with zinc atoms migrating to the inner part of the surface after the full relaxation, and the outermost layers being phased by sulfur, you know?
Okay, I understand. But this story, I think, is not so well in the manuscript. In the paper, is better.
Yeah, the paper is way better.
It's confusing in the manuscript.
Okay, I got it. Okay. History telling.
And
Okay.
one thing that you mentioned there, it's just about something about the basics of XPS that I want to touch, is that you discuss, I think in page 20 something, you read about the spin orb splitting of the zinc and sulfur. And you claim that, okay, it does not change it, and then you draw some conclusions from that.
You mean for all the manuscript or for all the paper?
On the manuscript.
Okay.
And my question is, do you expect the spin orb splitting to change?
Definitely not. No, definitely not. It's just information, useful as information, because yeah, you always keep in the same separation. I mean, from the zinc to P 3.5 to zinc to P 1.5, but sometimes the binary difference or the binary offset of the zinc and sulfur, it might differ a little bit, but essentially the spin orbital split, not at all.
Yeah, because there was a lot of discussion there that
There was a former paper that claiming to see some different splitting around 0.2 eV at lower energy, and I totally disagree with him. And that's why I prefer, okay, I have to figure out that our system is as expected 23 eV of separation between the splitting of the zinc 2p orbitals, and 1.2 and one, I think is 1.23 of the sulfur atoms. Yes, I just want to highlight the real position, let's say.
it's just that
Wait,
it's confusing whether it's just expected, so you don't have any experimental errors, or you would expect a change in the spin orbit splitting when you change the chemistry of your surface.
in that case, I wouldn't expect the change in the spin orbit splitting, because it's most likely a physics phenomena. I mean, they are well separated and they are containing more atoms in the 3.5 than the 1.5. You just can change the chemical state instead, rather than modification the way that the spin orbit is separated each other. So yeah, I can review this part, but I think
Yeah.
it's not important to discuss all the way.
Okay. It's just a point that I noted here. One other thing that I forgot to mention is, in general, it's not. I think you should make it clear in your text what is your contribution, what are the things you did, the experiments you did yourself, and you analyze your data. What are the things that were performed by collaborators or other people analyze the data? It's not
Okay.
clear for what DFT you did, what other people have done, what AFM if you or STM if we are made by you or for made by others, or
Essentially,
photoluminescence and everything.
I don't know if I've mentioned in the manuscript, I can review it, but essentially I did all the DFT calculations. Even for that former paper that Corinne did, the first this part here, which is in collaboration with Corina Rovel from UFSCar. But also I reproduced my calculation because she has the license for the VESP. I don't use VESP, I do Quantum Espresso. And so sorry, it's different methodology, different let's say package source, but keeping the same methodology behind it. And from the experimental point of view, I've just some collaborator performed the EFM and the photoluminescence, but I did all the analysis, of course, discussing with them. But yes,
okay, that's important to make it clear on the.
Okay, you mean now for alpha contribution after each section? Do you suggest?
Either on the text or you make a contributed, like people do a lot in the papers nowadays, that you say that what is your contribution?
Yes. But are you saying are you suggesting to include it be after each paper and the manuscript, or just make a, let's say, a small section describing what I did?
I don't know, this is whatever you prefer, but I think it's important. For instance, if you want to apply for a postdoc position and you give your thesis to somebody to read, this is one of the things that they are looking for, to see what you did, what you know how to do, and what was the work of others. Because it's good to have a thesis that has a wealth of results, but sometimes it looks like there was a lot of work of people, it was a work of a group and not of a person. And in this case, it was a lot of your work.
Yeah, definitely. I saw some theses of abroad institution when you have the cover part stating what you did for all the papers. I will make similar in my final version. And
I think it's important when you apply for a postdoc position, because it will emphasize that it was a lot of your work. You did this. It was not because most people will assume that theory was a collaboration.
Yeah, definitely.
Or somebody else in the group, or you did that, and you should make clear in your text.
Okay, perfect. I did.
I don't remember if you put in the text, but when you calculate the role of vacancies on the gap, I think was not in the yes. you did not mention that, but it's okay.
I have the density of state calculation in the paper,
yes.
But I don't know if it is inserted in the manuscript of the thesis. I really don't remember.
It's on the thesis, it's not on the presentation.
I prefer to skip because I've already discussed a lot on the electronic properties in the first part. So I prefer to focus here in the optical properties, because I was like wondering about the time, and then okay, I'm gonna skip some parts. Like in the same way, I just skipped the AFM discussion, as you noted from the part 3 of the paper. The several parts in the manuscript are not presented in this defense.
Okay, but the question I had, I don't know if you have the manuscript there, but when you put some zinc defects, you see states close to the valence band minimum, right?
Yes.
And when
Yes.
you put sulfur defects, you see the defect states close to the conduction band maxima.
Yes,
And you
definitely.
claim that in the case of zinc, you reduce the gap, but in the case of sulfur, you don't see a reduction of the gap.
Yeah, because there's a recently paper regarding the reduction of the gap as a function of the sulfur content that it's claimed that you need a high concentration of defects to form this to change the gap of the material. So
Yeah.
that's why in our case is in good agreement with the previous paper. And in the case of zinc vacants, we observed a match between the experimental conditions and the theoretical point of view when you don't need a huge concentration of defects to get modifications in the electronic properties in the band gap itself.
But your density of states show that you are changing the distance between the conduction band maxima and
No, I mean for when we have zinc vacancy, the concentration doesn't matter at all. When you have sulfur vacancy, you usually depend a higher concentration of sulfur defects to account for the modification in the band gap.
But this
even though
is an experimental result.
this
It's
one
not from your results.
is not from my result, is another theoretical
Yeah.
model. Yeah, yes. It's
So
older.
this story, you have to improve that.
Oh, what do you mean about it?
The way you discuss this, you have to improve in the manuscript
I see.
because you are jumping from one thing to the other.
I see.
And also, there's a lot of many times you mention that you have a sulfur-rich environment.
I mean, in the theoretical point of view, a sulfur rate environment just means to calculate it. I can back to this slide. To calculate it, let's see the pointer. Where is the pointer? Just a minute. Where is the pointer? To calculate it, the chemical potential of zinc, you have to choose if you are leading with a sulfur rate or a zinc rate scenario, you know. So basically, to compute this parameter, you have the total energy of the ZNS minus the 1.5 of the total energy of the sulfur molecule S2 in the box. So that's why I'm claiming I have the sulfur rate, because the sulfur rate we can compute the chemical potential of zinc atoms, which might be inserted in this equation to obtain the formation energy. So all these parameters is taking account this scenario. Of course, if you have the zinc rate scenario, I mean, let's say you put the zinc molecule or zinc atom in a cubic box, and then assume you don't have other sulfur around, you can compute the total energy minus the zinc total energy, and then you got the chemical potential of sulfur, you know. But it's way different because the μx accounts for the type of material that are taking out.
Yeah. I think you should clarify this in your text, because for me it was not clear at all whether it was something related to the theory or you're trying to reproduce your experimental conditions. That's all.
No,
You know,
yeah,
I have a sulfur-rich interface, and then I try to mimic this.
okay, I see.
You have to improve that. It's not clear.
Perfect. I appreciate it.
Yeah, so I can make a comment here. So actually, I already discussed with Pablo this. So if in the calculation you have to introduce more or less one species, but at the end of the day, we're not putting a atmosphere of zinc or atmosphere of sulfur. So
Yes.
for me, the correct physical term is always talk about this deficient of zinc or deficient of sulfur, because the UNUHV. So that would be like that has physical meaning. But zinc rich, what this means? I'm not depositing zinc, or it's not a vapor of zinc.
Exactly.
But from the calculation point of view, it has to put the, let's say, the atom in the box to make like this in excess or not.
Yeah.
But the interpretation should be crystal clear. It's a vacancy, so it's deficient of something, because the only thing we can do here, we're removing things. So yeah, I think this should be clear, or clarifying the text.
Yeah, it's just to make it clear that there are different meaning in the when you for a single crystal UHV and for the theoretical model that how you use to calculate the chemical potentials, because it's basically like that, right? How you define the chemical potential.
Yes, yeah, definitely.
You mentioned this in several points of the manuscript. The sulfur rich, as I mentioned somewhere, and there is.
Yeah, I totally. So basically, I just opened the manuscript here, and the equation is the equation 4.4. Yeah, I would describe it as this as zinc deficient instead of S-rich surface. Yeah, that would be better.
No, it's okay. You can put the rich as long as you make it clear that's in the context of the calculations that you want to reproduce, I don't know, the chemical potential or something, but
Yes.
for the single crystal in vacuum, you have the
zinc
surface
deficient.
that is deficient in zinc or deficient in sulfur.
Perfect. Totally agree. I take a note. I will correct it.
Because I think it's the same words are used for different things.
Yeah. Maybe the
It's
sulfur rich
different concepts.
it might be misleading somehow.
Yeah.
Yeah.
I have, I think, one more question on the CO2 adsorption. I'm about to finish. One of the things that you mentioned in the text, I think is, can you go back on the results?
Which one?
Yeah, maybe. I think you did not show there, but you mentioned that the first thing you notice is that this the zinc, there's a shift, and this is it marks the onset of reaction.
Okay. Yes.
You mentioned some in situ experiments like ours, a shift towards high body energy is a general interpret as the onset of a chemical reaction.
Yeah,
I
I forgot to call the reference. Yes, and maybe okay. Go ahead. Sorry.
I think it's overstating. A lot of things can happen when you put gases and temperature to an insulating sample.
Yeah,
Because you have charging, right? You don't have a very well defined initial state, so it's not properly grounded. And when you put gases and you have X-rays shining, it's like a flood gun, right? Internal flood gun. And you might change slightly. And if you heat your sample, so you might have changes that are not related to the chemistry or the reactivity. It's just different, just charging compensation.
Yeah, I agree. But this, let's say, overestimation in the text that's coming from because I had two samples, the defective and defect-free. So first I handled it the defective-free ZNS, and I didn't see any modifications during the heating. In the same way, by exposing the system to the CO2 or a combined atmosphere, I just start to see modifications under the gas, even under the gas and under the heating, for a particular temperature. That shift is not occurring for all the temperature. So that's why I was looking, okay, that's something related with the physics mechanism rather than only a gas shift or a fluid gun, as you perfectly said. Because otherwise, if it is most likely a gas shifting induced phenomena, I should note it the shift for all the scenarios, which is not true.
But it could be temperature, right?
Yeah, but the zinc sulfide, when you have the defective system, you have the gap of 3.6 eV. So you cannot promote states with KBT or even at lower temperature. So
but when you have defects, you can promote a lot of electrons by temperature, right?
Yeah, definitely. If you're looking for the shallow levels, I totally agree with you, but I don't have this calculation, so I can figure it out later. But at the first glance, I would say no, because I have the let's say the defective sample, and I was not expecting to see that shift increase that much, because if it was something related to the temperature, as long as I increase the temperature, I have to increase the shift. Do you agree?
Not necessarily. You're just populating states, and then you change the conductivity, and you have a different charging state. The way to test this is to heat the sample in gas or in the inert gas, or in vacuum or in inert gas, to see whether it's something related to the CO2 absorption that is causing this shift of the zinc, or is just a consequence of less charging because of different conditions?
Yeah,
my point is that sometimes you put like bold and strong claims, and you should be careful with that. There are lots of times in your text you have a huge impact or a massive and disruptive for the industry, and you should be careful with that.
It's just for motivation. Yeah, I totally agree.
Avoid the superlative.
Yeah, totally. Definitely, I would do it.
And my last question, can you advance, I think, 2 slides when you compare like physisorption versus chemisorption?
I mean, this one?
Yeah.
You mean this one? Yeah.
Like the interpretation of what's happening. I'm not sure if I agree with this weak physisorption and a chemisorption. If you compare the energies that you calculate, your CO2 adsorption energy is more negative than the oxygen adsorption energy.
Yeah, that's true.
So the first thing, when you classified physisorption and chemisorption, is the heat of adsorption. And it's like orders of magnitude. It's almost an order of magnitude. Usually when people measure that, because it's van der Waals interactions, delocalized things. Yeah.
Yes, I totally agree. But I mean, I had to figure out about this mechanism, but maybe I would say the oxygen stick on the surface. That's why I was claiming that is a chemisorption, because it stick and then go dissociated. But the CO2 doesn't stick on the surface. That's why I was claiming the physisorption. But I totally agree with you. The first parameter to compare the physisorption or chemisorption mechanism, it is the adsorption energy of both. Yes, I will correct this for sure.
Yeah, I think just avoid this classification, because this physisorption is either you have some issues with your energies, because I'm surprising that it binds more strongly CO2 than O2.
I can double check the results. I'm not sure. I can double check my DFT calculations, but
it was surprising for me, especially when you mentioned that you see that it looks like the O2 molecule is stretched a little bit, so you most likely have charge transfer.
Yeah, definitely you have, because this molecules has increased the bond length for, like, say 10%, almost. So it's most likely dissociating the oxygen bond. So yes, probably
I would expect this was so much stronger than the CO2 on this defect, but
yeah, me too. I
have to check that.
Yeah, definitely, but not. I think it is like the label is wrong. I typo.
Yeah, exactly.
Yes.
Okay, that's my last questions. I have the manuscript with the notes, and I send you later.
Oh,
congratulations for your work, both of you.
Oh, thank you. Appreciate your questions, Tulio, and all the kind suggestions.
Great, thank you, Tulio. So would you just make like 2 short comments? I think, I mean, especially when you approach the last chapters, you see that we are in unshattered waters approaching there, because it starts to become like the last results, and then so on. It's still like things to evolve, discussion also with Hannibal. But I think I discussed this with Pablo. So most of the things about the chemisorption here is it comes from the claim that the zinc reacts with oxygen in high temperature, and then you have zinc oxidation. Yeah. And that's why it gave some like experimental that, okay, it's oxidized, but there's conditions here for the DFT, 0 Kelvin, it's something else. It's just the molecule. There's nothing to do with what's going to happen in temperature and so on. So, and in principle, you don't do that. You just check the final energy of oxidized or not, is smaller or not. So that's why I think it's also tricky here to come up with so many of this understanding here just based on these results, because they're not exactly the condition we did the experiments. It's just like an insight, but I think we're not there. Yeah, okay, that was to address this, because I think we have to make it clear that the thesis, because otherwise we propagate this maybe like too bold claims later on. And I think the shift you mentioned, we discussed about that, right, Pablo? So also the idea of the walk
Yeah,
function
I was discussing
changing
yesterday.
at the temperature and the pressure. This make a lot of shifts, and then we have to really like stick to some relative energy position and see if we can really address this problem to make like this assignment of the peaks there. And that's, I think, is exactly what Tulio brought when in his questions. Right. So thank you, Tulio, and then I'm gonna call now our colleague Hannibal from the Brookhaven National Labs to comment as well and to argue, or not argue, to question Pablo about his thesis. So thank you, Hannibal.
Sounds good. Thank you, Fernando. And a great presentation, Pablo. You did a really good job. I echo some of the general comments from Renata and Tulio on the quality of the presentation, and the manuscript needs to be improved a little bit to match the quality of the presentation. But my comments would be like in general lines to what Renata and Tulio mentioned.
Okay.
I'll skip that part and go straight into the science questions. So I was wondering if you have a good idea on, so you're losing zinc when you're making the defects. What is happening to that zinc? Or is it sublimating, going into the bulk? Do you know?
The first glance, I would say it's go away all the way out and sublimating, because the bulk seems to be still zinc deficient, since you perform some photoluminescence spectra, and it is like most likely bulk sensitive. And according to the DFT calculation to support these experimental results, the zinc vacancies at the bulk is the most stable one. So I would say the zinc is most likely sublimating another species.
Okay. For the DFT calculation, you have that the zinc defect calculated in the first layer. From the experiment, like that's not known where the defects are.
Yeah, definitely not.
Do you? Yeah, that'd be interesting to, and I don't know if how. I guess you haven't done these calculations, but I was wondering if you have any ideas on how would the chemistry change if your defect was in the second layer? Would you have similar behavior or not? Would it be too far and it doesn't have an influence? Is there something interesting to address?
Yes, actually I did like a subsurface vacancies, and I didn't note appreciable modification on the total energy and the mechanism where the molecules interact with the surface. But one thing that I didn't yet is to explore the increase the number of vacants, like performing one vacancy at the first layer and another one at the subsurface. This one might be insightful, because as long as you have more vacants, of course, you're gonna have a higher absorption of molecules, as you demonstrated for all this thesis. Another strategy is just increase the slab and then increase the number of defects to keep the ratio almost the same, but just changing the place where the vacancy is. It might be useful, but I don't know what is happening. Probably this molecule is gonna interact close to the mid atom in the slab, because as you noted here, the CO2 is pointing toward the zinc vacancy on the top layer. As long as you take out the second layer atom of zinc, probably might like, let's say, displace a little bit for the inner part, and I don't know, it might be the same behavior but with different aspect on the molecule. I have to do the calculation actually. But it's an insightful idea.
Yeah. So you mentioned you did do a calculation for a second layer. only.
Yeah,
Is that vacancy more stable in the second layer or in the first layer? The
from a
vacancy
calculation,
with no adsorbates. Yeah.
it is easier to take out the vacants on the top layer because it's already uncoordinated zinc atom, But it's not that much the difference between of the first layer and top and second layer total energy. Just comparing the system with vacants without molecule, as you said.
And so here you have one out of what is the population? I guess we're seeing just one layer from the side view here. What is the population of defects in this case, in this calculation?
Where?
How
You mean how
many?
much defects I have?
Yeah, what?
I have I have one defect over 32 atoms, so it's 1/32. It's below 5%.
Okay. And is it similar to what you had in the experiment?
Exactly. I'm supposed to have like I below to 5% of defects experimentally, so I try to keep these ratios so close.
I thought it was larger from the experiment. In at least from the XPS, which is not surface sensitive necessarily to the very top layer. But I thought the difference between zinc and sulfur was more than 5%. Maybe I remember.
No, you have 16 atoms of zinc, 16 atoms of sulfur.
No, in the experiment, I mean.
30, the experiment, I don't know. I can't
No,
quantify
you can go back the image. Yeah, stay slide. He's mentioning.
because this comparison is a relative comparison. You cannot claim that you have like 10% of sulfur over the zinc because the zinc is most like bulk sensitive. This is zinc 3p. Of course you have this signal for surface, but it's like just indicating the preference of the atom, which atom is pulled off from the surface, if sulfur or zinc. So preferentially sulfur stay in the surface and zinc is pulled out. But I cannot claim from XPS the amount of defects that I have. So
Okay. It would be interesting to do the low energy ion scattering. Then you would get.
Yeah.
We didn't think about it when you were here. There's one of the instruments that has low energy ion scattering here. But yeah.
That would be great.
Okay. So do you think you can tune the number of defects experimentally? So you got to certain you were showing us a function of annealing temperature in this plot here. Is it like if you keep it longer at, let's say, at that temperature, do you get more defects or you reach a stable amount of defects at each temperature?
I think there's a limit because when I did, let's say, take the same sample again, 1:1 ratio, and then go straight to the 1420 Kelvin, and then increase a little bit just to 1420 as the second paper. We didn't know appreciable increase on the sulfur content over the zinc. So I think there's a limit when the surface defect gets stabilized on that ratio, and there's a threshold in temperature, I guess.
Okay. Yeah, I was thinking from the thinking of the practical applications on the defect engineering. If you want to think of it like using this material, are there ways to tune this the number of vacancies and because I imagine you would get different behaviors for different populations of defects.
Yes, one interesting strategy, instead of still working with native defects, is like, once you reach the threshold of the temperature, you might decorate the system with other nanoparticle like palladium or platinum and so on and so forth. That also its potential is promising to improve the number of active sites. It's like mimic the increasing of the population of the active sites on the surface and made also play a role on the other property that I showed off in this presentation. But I think now it's time to move forward and try to combine, still working with the band gap engineer, but combine with other systems like nanoparticles or even other thin films, you know.
Mm-hmm. Yeah. Yeah. So, so now, like in line with this discussion on making defects, how would you do this if you had let's say you found this material is very useful for certain practical applications? How would you prepare a bulk version of it to use in the industry that has this level of defects?
Honestly, for hero word applications, I have no clue. I just have my solid state physics point of view on how to control these vehicles. Uh, Ideally, if you have somehow there's some furniture to heat it up your system under a controlled atmosphere, you might undergo in this let's say zinc deficient ZNS, which seems promising for this wide range of application. But of course, in the real world, we will gonna lead to with impurity like carbon and nitrogen and other impurity that is not present in our system, both experimentally and theoretically. So effectively, I need the help for the engineers.
Okay. Yeah, no, it's good. I was asking this question because we tend, like, I remember from when I was doing my PhD, we like tend like to focus on what we are doing in the research, and it's easy to lose perspective of reality and how what we do fits in the context of the real world. So it's good while you're doing the research, also think on what could be the implications, or if you had to scale this up, and like the ideas you were mentioning on the furnace are very reasonable. And as you mentioned, even if you have some vacuum furnace, you probably have the oxygen in the at least 10 to the -5 millibar pressure range with the roughing pump that you use in those ovens. And you were showing very clearly that when you have, I think you have 10 to the -5
Yes,
millibar oxygen, you are already oxidizing the surface, so you're not going to have your intended surface even when
yes.
using that furnace. So you would have to get I guess an ultra high vacuum furnace if you just wanted to get the zinc defect without having the oxygen. So these are things to consider from the engineering point of view when you translate to the real world. And something to think about.
Perfect.
For the CO adsorption experiments, you were showing that before putting the CO2, before putting the CO2, there was no carbon. And then when you put the CO2, you don't just see the peak assigned to CO2, but you see this other peak at around 285. Those aliphatic carbon. Where is that coming from? Because it wasn't there before. Is it?
Yeah, my claim
The
is
CO2 was contaminated.
no, my claim is when you heat up the system at grid V, probably you generate water from the chambers and they go relaxing the system toward weight V again. Those water molecules in the chamber just stick partially in the surface. So it's most likely water disturbing from the chamber to the sample. But as you noted here, is not that much at this condition. It's like 6% of the total area. But yeah, that my claim is coming from the water disturbing from the wall of the chamber.
You mean the carbon in the walls of the chamber that is pushed from?
Most likely, I guess.
Carbon.
Yeah, I mean, like, where's the carbon coming from?
Oh, first, you have the carbon derived from the CO2, but also the carbon is not, the CO2 is not sticking properly in the surface. So there are several, let's say, a bunch of carbons around from the CO2, and like some of them are surrounded by water molecules that absorb on the surface. So it seems like you have the CO2 interact with the defectives in a surface, but this NS surface also contains like water molecules coming from the dispersion of water from the chamber. So you probably you have the contribution for CO8 bond, as you noted from the oxygen, and also from this carbon contribution here. That's my first guess, actually.
Yeah, no, I wasn't talking about the OH group. I was talking about the other carbon.
Yeah. Huh?
Okay. Do you think it's just contamination from the chamber or from?
Most
Okay.
But Pablo, he's talking about the aliphatic group, the red.
The red
Component,
component, the huge red component there. This is
No, the red component is the carbon-carbon interaction. It's a sp3 carbon. It's not the
Yeah.
contamination.
Yeah, but where is it coming from?
where does it come from?
You have several CO2 molecules interacting each other, so
Yeah,
probably
no, I
that's
don't think it's from the CO2. The CO2 is not going to break apart there.
Because that
Ah.
means that you are breaking the carbon-oxygen bonds and making carbon-carbon bonds.
Yeah.
Oh
This
yeah,
is
that's
a-
not
Yeah, no,
that's
that's
not
not happening. Yeah.
that's not happening. Yeah, definitely not.
Yeah, I don't know, but so this
I
is
don't
the sample, like the before is right after sputtering your sample?
What? Sorry. The before, yeah, I spotted an anneal in the sample in the
Okay.
ATV. Yes.
But okay, and then the one that's the one at the bottom, and then the one on top is annealing in CO2, right?
Yes, perfect.
So if you anneal with no CO2, do you see that peak?
But annealing at with pressure at UHV?
Yeah.
No, there's no peak.
If you anneal to 5, no, I was thinking if it can, if the
I
carbon is coming from the bulk, for example.
Yeah, I can. Yeah, probably you can. I can show you this data. For the oxidation, I heated up the system at -5 millibar of oxygen, so there's no carbon peak.
Yeah, but if you hit in oxygen, you're burning the carbon.
Yeah, that's true. That's
If it's coming from one source, it's either coming from the bottom or it's coming from the top, right? It's coming from the chamber, contamination in the chamber, or it's coming from the bulk of the material.
yeah. I have to figure it out about it.
Yeah.
I don't know.
Okay. Something to consider. Yeah. I mean, it probably doesn't. It's not that relevant to the whole story, but
No, it's
something
important to mention about it. Yeah.
to have a paragraph in the manuscript discussing where it came from, because this for the paper that you're preparing, that question
Yes.
will very likely be asked.
Definitely will.
And the oxidation experiments, those were on the surface that is already defective, right?
Yes.
Okay. In slide 24, where you had the DFT for the adsorption, you had an oxygen adsorb, and then the CO. Is this 24?
It is 24.
There was one that it was written 24 on there.
Because I skipped the count for the slide in this.
Oh,
in this
okay.
one.
Okay.
This one, I guess.
Okay. Oh, they're okay. So they're not in
the 24.
Okay, there's more than
That
one
is the
24.
true.
Okay.
That was the former one pretends to be 24, but this is the
Okay.
true 24.
Okay. So you have the steps here. Do you have like the energetics of as you're going through these steps?
I'm calculating. It is that the NEB calculation is running. I don't.
Oh, God.
I
So
don't
this is not finished.
No, this one not.
Okay.
You mean the climb image between the computing the transition state, because what I have here is just the evolution, taking account all these steps, but I didn't calculate the number of each step, I
Okay.
had to do it.
But so you're doing okay. So but you have the energy for each of these states. Now you're doing
Of
the
course.
transition states, right?
Yes, perfect.
Okay, but do you have? It would be good to add to this the energetics.
I will include it. You mean to include this in the final version of the thesis?
Yeah, well, I don't remember in the thesis if you have this
No,
figure
I didn't include.
accompanied by the energy of each of these structures.
No, not yet. It's not ready yet.
Okay.
Because also I have to calculate the core dissociation energy, because you have a new term derived from, because now you have GNS oxygen, the oxidized GNS surface, and then you have the CO. So I'm figuring out how to calculate the core dissociation energy, and then I'll move forward to compute the energetics itself.
Okay, right. You'll need that for to validate the proposed mechanism that you have.
Definitely, I need, yeah.
Okay, I think those are all the questions that I have.
Thank you, Aníbal. Thank you
Thank
for
you.
support along the way.
So yeah, great, Aníbal. Thank you for your comments. I would have a question for you, Aníbal, actually, because I was not so surprised about the cobalt, the carbon CC group there, because if you put, for me, these components are gonna always be there. If that's swap, we can argue how much, right? So this is too dirty or not.
Yeah, I was surprised it wasn't there before.
Yeah.
Right.
Yeah. Oh, okay, yeah. No, but before when we do at this conditions, or Pablo can argue this, but because he did it, but I just saw the data. But 10 minus 6, 10 minus 5, and 10 and annealing, you don't see that. This happens if it's auction. If you put CO, you put CO2, you put water, and then you can argue how much you have in periods and so on level. Also, I think here would be nice later on that Pablo also, when finalizing this data analysis here, that we quantify how much carbon we're talking about here, because it should not be much, otherwise it's really like contamination from different sources.
Yeah, it's almost negligible for the survey.
Yeah, but to get to the number there, it's 1%, and this is pretty low, because this would be nice because the argument would be always these components at the left side, right? So it should be play safe here.
Yeah,
but
especially because you have 10 times more of the unwanted carbon than the CO2 that you would like to see.
Yes.
Yeah, so that's why. So for me, it would make always more and give more confidence about this type of data in an NAP regime or ambient pressure regime. Is we are looking at elevated temperature, at elevated pressure, and let's see. We know that the components, the signal is much smaller, but then you don't have this argument that it's later on, it's afterwards, that things unwanted water comes up and so on. Would be nice to always try to evaluate this type of data at the temperature, at the pressure. But we know that's also your fight with intensity.
Yeah, it's ongoing. You did it at Brookhaven, but the data is not showing here. You do next for sure.
Yeah, it can always be that during you have one species, after you have another one, maybe they make sense, maybe they don't make sense. But if there is some sense at the conditions, pretty sure that's correct. Afterwards, you can always have a lot of discussion about if this is real or not, right? Because it's the leftover. It's what happened after, and it's not at the condition. But who knows now? I would have also some questions like friendly fire, but not that much. That I think would be nice that Pablo can clarify, because I think a point that maybe is not clear in the text. Okay. So I would start backwards, because Tulio and Hannibal, they discuss about like this story about the defects, where the defects are, what they are not. And I think in our discussions, we had very clear that in the first chapter, compared to the second chapter, there was a story that has to do to identify where the defects are. And the idea of the first chapter and the second are a bit different. So in one, you are very soft in the annealing treatment, and then you create the so-called zinc vacancies.
Mhm.
But then in the second one, you have a goal there. What's your goal in the second part of the second chapter?
It is
So
to explore
it's the same goal of the first chapter. So because this has a little bit to do with what they ask
yeah,
about
because
defects, where they are, and so on.
yeah, the goal is quite similar, but in another perspective. Let's say from bottom to top. If you explore the role of defects at the surface, we now explore the role of defects at the bulk level, because we wanna. The question is, does the defect extend to the bulk, or are we limited to the surface? That's what the first question that motivated us to move toward perform that experiment that you show. And then calculated the properties that taking account the zinc vacancy at the system. So essentially, it is the difference here. Looking for the bulk and a throw out perspective from bottom to top, surface and bulk.
Yeah,
Surface in the
because
first part, bulk in the second one.
yeah, but because I think you didn't mention this to them now in the replies. For instance, Hannibal
I
ask you, why did you consider defect in the subsurface? And of course, this makes sense, but it is a condition that is achievable or not. Can you create a
experimentally,
defect only in the bulk?
no,
I mean,
because
with the tools you have.
yeah, I mean, from the FT as an Ibo asked, you can
Yeah.
control where you pick it up the zinc atom out. Experimentally, you cannot control the portion from where the atoms is pulled out from the surface, you know?
But could you think about some preparation procedure that you create vacancies and you put a little bit of excess zinc on the surface, evaporate zinc on the surface?
That'd be great. That totally be great. Me and Fernando had that discussion that feature works on this regard. Like if you have some MBE evaporator for zinc atoms, you can like pinning zinc atoms at the top, at the surface, and then you can promote the zinc rate surface. Then you can control the amount of defects properly, and that might be a good play away in the near future. But yeah, I didn't perform it.
Right. Regarding we talk about the zinc vacancy, but regarding the morphology of the surface, I mean, like you did the several cycles of cleaning, and then you did not mention too much to the people here. Can you discuss a little bit how this would affect the interpretation you have, even in the DFT, because you are calculating a defect on the surface, but
Yeah,
the surface at
I
the end
can
of the
I
day
can
is not the same.
yeah. You can note here in this panel that the sulfur atoms are most likely shifted to the outermost layer, because typically, as you mentioned in the first paper, I go back just a minute. Your surface undergoes some reconstruction. This kind of reconstruction means that the sulfur moves outward the surface while the zinc stays on the moves inward the surface. In terms of morphology, the morphology of the system is we are altering the way that the terraces interact with each other. As long as you increase the number of defects, we are promoting more terrace at the system, like increase the vicinity of the ZNS surface, which might help to trap the other molecule like oxygen and CO2 and CO. That's why we have this AFM file. Let me see if I can open up the thesis shortly. I'll quick move for the AFM part. Oh, this is the draft for the paper, sorry. I think this is my thesis. Yes, this is the morphology of the system before doing the treatments that you got, and then you have the vicinal surface with several terraces well separated, and this is most likely an effect of the sputtering annealing of the ZNS surface at high temperature. I prefer to not discussing this in this presentation because it doesn't play that much role at the effect that you have on the analysis and the whole history that I showed today. But yeah, this is the effect of the morphology itself.
Yeah, I think it plays a role like that. You cannot simulate all these defect structure because at the end you don't know, you can get the angles or whatever, but you would have like different sites available. The
Yeah,
TFT is a simplification of the problem. That is
Yeah,
right. So I'm just create some defects here, but you have much more reactive sites there. So
Yeah.
this is
Yeah,
something that we know, but and maybe we should like make a comment when we finish this work about the CO2 reactivity and CO reactivity.
yeah, that'd be great. Can make it.
And just I have other points here, but I think we have to move on also with the committee. But you gave a answer to Professor Renata in the beginning that I'm not sure if I understood correctly. You said something about the OG peaks, and you did like a statement like, "Oh, the OG peaks is not the OG peaks of the ZNO and not from the ZNS." And I didn't get this. So can you explain me better this? Because
I mean, Professor Renata has mentioned about in the ZNO-ZNS, you are not able to deconvolute the contribution for ZNS and zinc oxide. What I was claiming before is when you have the ZNS, you have this shape with a strong shoulder toward high kinetic energy, but the shoulder disappear when you oxidize the ZNS, obtaining the ZNO-ZNS. So of course you have the hybrid interface, ZNO-ZNS, but what I said is you cannot disclose the contributions from the ZNO and the amount of contribution for ZNS, you know. You just can note the change in the shape of the peak. That's what I say with Professor Renata.
No, okay, I see. But you cannot do that, but maybe because we don't have like a good a fingerprint for the shape of the OG peak as we have for the modeling of core level peaks. But
the first option
clear
is
for
this.
you that you say, like you said again, like hybrid interface for the spectra here. Doesn't matter if it's hybrid. If it's like a component A and B or a mix, if it's not like a ternary compound, zinc, oxygen, and sulfur together, it's like a linear combination of the two spectra.
Most likely, yes.
It should be, because otherwise you discuss with Tulio, the core level peaks, they are the same distance when you did all these things, right? Because it's zinc in that environment. So if it changes, it means it's not anymore linear combination, it's another compound. So here, for me, that's why now you clarify, but it's clear that you have zinc oxide on top of ZNS, or whatever the order, it should be a linear combination of these two peaks. Maybe it's too complicated to account for the shape, maybe not, but I think the message here should be clear that they are simply the spectrum of ZNO plus the spectrum of ZNS. If you have more ZNO on the surface, you get more signal. If you have more ZNS, you get more signal for ZNS.
I see.
Right.
I see.
Yeah. Great.
I don't know if I agree with you.
Why?
Why? Because maybe I don't have really any clue that it is a sharp interface there.
No, but it is not sharp. It should get the signal of one and the other. I mean, like with the right ratio and so on. It's not sharp.
I'm not sure about this. I think we should talk if you want later. But I'm not sure. Maybe you have really a mix.
Okay, then that's a good point. So I think Pablo can answer that. You have a mix, Pablo.
You definitely have a hybrid interface. So there's a
No,
ZNOs and F contribution.
this is like titles for Nature papers, a hybrid interface. That's not. It's a mix. It's a ternary compound. What is this?
No.
With your data,
No.
you can.
Effectively, this is the oxidized ZNS surface. It's not a fully covered ZNS, like a bulk ZNO and bulk ZNS. It's like few layers of ZNO covering the ZNS,
Yeah, but look, you see in the convolution two signals of zinc 2p, correct? That's what
Yeah,
you claim there.
because the zinc 2p is the most surface sensitive, so you can account for the contribution from the
Yeah,
top
but
surface.
that point that Renata rose. So you have some other evidence that is not a combination of zinc, oxygen. Let's create a compound, zinc 2, sulfur, oxygen. Do you have any evidence that it's not that? I think the data is here, it's in front of you.
The evidence is like the sulfur is not formating sulfate. So I don't know, probably you only have the ZNO, the same zinc atoms that are coordinated by sulfur. Now there's lower sulfur that's available at the surface, and now the zinc is also coordinated by oxygen. So indeed, you have the evidence that we are not formating like ZNO and ZNAs in a coexistent phase. I would say that. I don't know what you point you want to raise it.
Yeah, no, but that for me that's the point. So it's the sulfur show
Okay.
the signal that is the sulfur bind to oxygen. No,
Yeah, no,
to
there's no
zinc.
sulfate.
Yes, just zinc. You
Yes,
see the signal of the oxygen that is
yes.
binded to where? To who? To the
To
zinc.
yes.
And then you look to the zinc and C2 component. So you have something that's separated. It's not ternary. And at the end of the day, this means that all the spectra you see should be a linear combination of these things,
Yeah.
depending on
It,
how
might-
much
it
you
might
cover or
it
not.
might be strong heterogeneous. You might have islands,
Yeah.
so you have a lot of interfaces. So the surface interface area might be high, and that's why it might explain why your zinc-rich signal is not exactly like the ZNO single crystal, because you have a lot of defects and a lot of it's a defective structure. It's not the ZNO single crystal after sputtering annealing.
Yes.
So then you have broadening, and then you might lose some features, but it should be. I think if you work on the binding energies and the quantitative XPS, you can rule out the idea that you have a homogeneous mixture or a ternary compound or whatever.
Right. So, from my side, I'm happy, and then if everybody's happy, so we can ask Larissa to give us some times and discuss about the defense of Pablo. Thank you, Pablo.
Tá, vale, é só aceitar na tela de vocês, tá? Para ir para a sala simultânea.
Larissa, eu fico na sala com uma.
Pode ficar aí, tá, Pablo? Só aguardar eles voltarem.
Tá bom.
Pablo is there? Oh, great.
Yeah, I'm here. Yep.
All the committee is there. Unfortunately, Hannibal had to leave, but then he transmits his congratulations to you because the committee decided that you approve it for your to finish up to obtain your title for the doctorate. And I would very much like to congratulate you in person, but
Yeah.
then you have just this chow here. Congratulations, parabéns.
Thank you. Thank you.
Congratulations, Pablo.
Thank you all the committee members for the comments and the suggestion. I'm gonna improve it, my text, and I hope to see all you guys around. Chile and Synchrotron and Wi-Fi Jota. Also come to CBPF. I'm still working for a little bit with Fernando, and yeah, that'll be all. Thank you for all the people that supporting me during the journey. It was tough, but yeah, we got finally.
Right. Yeah. Great, Pablo. I'm not sure how it goes now because Larissa has to send us a document to sign, I guess.
Eu envio o documento
Yeah.
por e-mail, tá? Para todo mundo assinar.
Okay.
Pode botar a assinatura do
We do
Gota, tá
later
bom? Tá, vale.
Yeah. So